Alright, let's look at one where we have got to do a little bit of thinking, a little bit of work before we can actually jump in and do the integral. So if I'm looking at this and I was told to evaluate this, find the volume underneath the function sine x over x. The problem is sine x over x with respect to x, that does not have an antiderivative. We've seen that one before. In Calculus 2, you had to approximate this when you were doing like when you were learning like integration by parts. This doesn't have a closed form antiderivative. So what we have to do is look at our region. Remember, these are y's, 0 to 1, and these are x's. Right? X equals y, x equals 1. So let's look at this really quick. So in the Desmos, I just typed all the different things that show up in the integral. So we have x equals y, x equals 1. Remember, that's these things. X equals y, x equals 1, y equals 0, y equals 1. So I typed all those in, and I get all these different lines. But remember, what we're doing is finding the region where they're all bounded. So where are these all bounded? And if you look, there is my bounds in the x direction, my bounds in the y direction. This right here, this triangle, is the region that I'm working over. And so right now when we can't do the integration, we've got our changes set up like this. Y is the outside going between 0 and 1, right? That's the outside. Those are y's going between 0 and 1. So y equals constants on the outside. Those are illustrated by this horizontal line. Y equals a number, the horizontal line. And the x's are restricted to x being equal to y. Right? So for these are y, 0 to 1. So x is less than a is less than 1 on the top. And notice that's what we get. We get these horizontal lines. Well, the integration is not working in that direction. So what can we do? Instead of evaluating it left to right, now we can make x, because again, we're just trying to get this region. If we make x go between 0 and 1, which defines the leftmost and rightmost boundary for this region, we can make y vary between 0 and the current x value, because this line is y equals x. Right? So if it's x equals y, it's also y equals x. And now we can make our integration go between these two curves on the bottom and top, rather than those two curves on the left and right. They're still defining the same region, but we're doing it vertically. Vertical changes as x goes between 0 and 1, instead of horizontal changes when y goes between 0 and 1. Okay. This happens a lot, that we have to change our order of integration. Our order of integration was between these two regions first in this range for y's, to now these two curves first in the range from here to here for x. We're describing the same region, we're just doing it in a different order. So this is what we started with, but the order of integration with dx dy doesn't matter. If we switch the order of integration, we can now go between 0 and x, like this picture is showing. All right, what are these y values? The y values are 0 on the bottom and then y equals x on the top. All right, so we're changing the order of integration. This is what it was. It was going between x on the, as y goes between 0 and 1, what's the leftmost point? The leftmost point is x equals y, so the y coordinate, to 1. Right, that's what we had before, and now we're switching it to 0 on the bottom and then y equals x. So 0 to x on the top. And that's what this notation means. It means this is what we're being asked to do. Find the volume underneath this surface over this region with respect to any order. dy dx is dA. This is a tiny change in x. This is a tiny change in y. They're being multiplied. Length times width is area. So this dA means just multiply them together. You can multiply in any order you want to. So this changes the order of integration. But when we change the order of integration, when y comes first, then x. Here, x was varying between a line and a vertical line. Well, here they are. We change the order of integration. We remember we have to finish up with constants. So now x has to finish up with constants. So that line that we saw has to be described in terms of y now. So x equals y is the same as y equals x, right? It's just our order has changed. So this is our new limit integration. Well, we can do this. This is a constant in terms of y, so what's the antiderivative? You just stick a y on there. This is a constant, so we stick a y on there, and now y is going between x and 0. When I plug in x here, the x's are going to cancel. When I plug in 0, that's all going to go away, and we're just left with the sine function. And we can integrate that all day long, and we get negative cosine. Plug in 0, plug in 1, then plug in 0. Cosine of 1 is not an exact value, but we can approximate it. And there's our answer. And what we've just found, again, let me move this over a little bit. That was our region. Instead of doing it left to right like we had been set out to do before, from the line x equals y to x equals 1, now we're doing it from y equals 0 to y equals x. Okay, we changed the order of integration, and we got something that we could do. Previously, before we did this, we couldn't do this integral. We went from impossible to doable. Not just doable, actually very easy once we plug things in there. So the important thing for you to understand here is with multiple integrations, sometimes we have to change the order of integration to be able to do the problem. Or if we are setting it up blindly, maybe it wasn't set up for us and we changed the order. When we are setting it up ourselves, we have to come up with ours. There are times where we could come up with something that just doesn't work, and then changing the order would make it work. So we have to be really careful about how we set these things up.